Good morning, all. Good morning. I am audible.
Good morning, sir. Yes, sir.
Am I audible?
Yes, sir.
Audible, sir?
So, welcome to the day 3 of our GIAN course. So, today we will be having 2 sessions on chromatographic technique, specifically ultra high pressure liquid chromatography and then mass spectrometry. Because these 2 techniques, they are very efficient as when it comes to analysis of or quantification or detection of substances or any substance, maybe organic of organic origin or some you see complexes of biological origin of synthesis origin. These techniques they can detect this type of compounds even up to a concentration of picograms. And as the concentration of contaminants in these you see samples, environmental samples, maybe water, maybe air, they are very less usually because the dilution factor is very high for certain contaminants. So we need very sensitive and those very sophisticated methods. There's LC and MS, LCMS we call it. That is the most effective one. So we have split this total technique into 2 parts. One is liquid chromatography, specifically UHPLC, and the second is a mass spectrometry. So here we will discuss about the various aspects of UHPLC, why it is so efficient, what makes it so efficient, and how it can be used. And then we will start with the mass spectrometry. What are the different theoretical aspects related to mass spectrometric analysis? So coming to the first session, so analytical techniques for contaminant analysis, that is UHPLC, ultra high pressure liquid chromatography. So contaminants diversity, we know we have in the last 2 days, we have seen that the contaminant diversity is very vast. There can be metals, then there are many inorganic compounds, then there are numerous organic compounds. Those compounds may be volatile or non-volatile. Those organic compounds may be belonging to the category of pharmaceuticals, personal care products, plastics, or of natural origin, of pesticides, of any class. And then gases. There are certain gases also which are contaminating our environment. So to cater to see this huge diversity of contaminants, we need a single analytical technique is not possible for its purpose. So we use different methods for analysis, and these methods are classified basically into 2 categories: wet chemical method and instrumental methods. Wet chemical methods are the conventional methods which we follow in the laboratories, like flame test, which is a very specific for metals like sodium, nickel, cadmium, zinc, manganese. So they give a specific color in the flame, which helps us to analyze, to detect what type of element or metal is present in the sample. Then volumetric analysis means we call it a titrimetric analysis, particularly the precipitation titrations. Then gravimetric analysis, So these are conventional methods which are used for certain inorganic salts and some metals. Then instrumental methods, they are different three types basically. One is electrochemical, then spectroscopic and chromatographic. Now there are certain species which are electro-reducible. They undergo redox reactions under the influence of electric current or potential, and such substances they are very efficiently detected by electrochemical techniques like polarography, like voltammetry, like pyrometry, and so on. Then spectroscopic methods, they are basically of two categories. One is absorption, one is absorption and emission. And further, depending upon whether we are dealing with atoms or molecules, it is atomic absorption or atomic emission, and molecular absorption or molecular emission. So atomic absorption and atomic emission spectroscopy is again a very sensitive one. Although flame test is there, it is a qualitative, but atomic absorption and atomic emission, they are very efficient quantitative methods for determination of different types of elements like sodium, potassium, cesium, mercury, or so on. Then absorption spectroscopic methods like UV spectroscopy, IR spectroscopy, NMR. NMR is usually used for the qualitative purpose. Then spectrophlorimetry. So out of these, the UV visible spectroscopy and spectrophlorimetry, these are the most common methods, and they are very sensitive method and very efficient one for quantification of different types of organic pollutants. Then chromatographic method is another instrumental method. So basically, chromatographic methods, they are not analytical methods; they are the separation methods. So they separate the components into individual, separate the components in a sample, so that each component can be analyzed by the spectroscopic method. So this it is you see a hyphenated technique. Now we can say chromatographic spectroscopic methods. So depending upon the different components of a chromatographic system, they can be gas chromatography, ion exchange chromatography, size exclusion chromatography, supercritical fluid chromatography, then inductively coupled plasma chromatography, then HPLC. And HPLC is further different types depending upon what type of hardware is used. Like it can be normal phase chromatography, reverse phase chromatography, ultra high pressure liquid chromatography, and highly chromatography. So we will be concentrating more on the liquid HPLC and UHPLC because these are the most common techniques. Around more than 90% of the chromatographic analysis on contaminants, they are performed using HPLC or UHPLC. So what is a chromatography? It is a physical method of separation in which the components to be separated are distributed between two phases, one of which is a stationary phase and another is a dynamic phase, which moves in a definite direction over a stationary phase. So this is the official definition of chromatography as per the UPSC. So this is the so wherein uh, uh, apply a particular the sample as a spot on a TLC plate, and when it is run in the mobile phase, right, it is separated into component. For example, in this case, we have shown how a black ink is when it is run with the help of water, it is separated into its three basic colors: cyan, red, and yellow. Right. So this is the anti-gravity chromatography. We call it thin layer TLC, thin layer chromatography or TLC. Then there is another type of chromatography which moves with gravity, like column chromatography. So wherein you see again we have taken not a plate but we have taken a column which is looked like a syringe, and in that we fill the mobile stationary phase here, and on the top we apply the sample. Let's say it is black ink, right? And then we elute it with the mobile phase, and see the components they start eluting. So first the yellow color will elute out, then the red color will elute out, and then the blue color elute out. So this is see with gravity we call it a column chromatography. Third type of chromatography is unrelated to the so here the stationary phase in a tube, and it is you see then the sample is loaded on one end, and the mobile phase is entered from that end where the sample is loaded, and it is some pressure is applied to make the mobile phase pass through the stationary phase. So when the mobile phase passes, it carries away along with it the components of the sample, and depending upon the affinity of the components to the stationary phase and mobile phase, the component get separated. This is called. So how these components are separated? Which is organic in nature, and it is applied by the mobile phase. So mobile phase is you see pulling the solute in the forward direction, but at the same time this solute is dissolved onto the stationary phase. It is adhered to the stationary phase through certain interactions. That may be hydrogen bonding interactions, that may be ionic interactions. So because of those interactions, this solute may adhere to the stationary phase, so it is a retarding force. So this adherence is retarding the movement of solute, and movement of mobile phase is pulling the solute along with this. So depending upon the you see which force is more predominant, whether impelling force is dominant or retarding force dominant, the solutes they move to the different extents, and as a result they get separated. Now there are the basic several mechanisms by which through which the chromatographic separation is takes place. Like a partition is there, then adsorption is there, ion exchange is there, size exclusion is there, and affinity is there. So depending upon what is the nature of the stationary phase, what is the nature of the mobile solute, we select a particular type of mechanism by which we can dissolve the components. Like in partition phase,
Excuse me, sir. So you need to unmute your. You
Okay.
need to. Yes, yes. Thank you.
So should I move to the previous last slide? No?
Yes, sir. Yes, sir.
From where?
So next one. Yes, from here.
Okay. This is the difference between you see end capped completely end capped column and incompletely end capped mobile stationary phase. And see here the two components, dextromethorphan and hydroxybenzoate, they are not completely resolved. But when we move to the completely end-capped system, end-capped stationary phase, all the three components are resolved to the baseline resolution with very distinct peaks. So that is the advantage of complete end capping. And nowadays, all the stationary phases which are coming to the market, which are available commercially, they are usually end capped. Another important factor is when the bonding parameter of the stationary phase is the bonding density. So this is the only measurable parameter which is related to the quality of the bonded phase, right? And it is a called carbon loading. Means how much carbon is present on the stationary phase. So this is the percent weight by weight of a carbon atoms bonded to the silica surface. More is the number of carbons attached to the more bonded to the silica surface, right? More will be the bonding density and better will be the resolution. So more number of carbons are attached to the silica surface means more is the end capping. So bonding density is the number of bonded ligands per unit surface of silica, right? So analytical columns, HPLC columns, they are available in different sizes or different diameters, depending upon what our needs are. They are selected of the they are selected as per the need base. Then this is there can be, you see, three types of column. One is an analytical column, then there is a micro column, and there is a guard column. Analytical column, they are usually of 5 to 25 centimeter with the particle size being 3 to 5 micron and its a diameter being 3 to 5 mm. And they usually have 40,000 to 70,000 plates per meter. And micro columns, they are usually 3 to 7.5 centimeter in length. And they are micro bow, means they are 1 to 5 mm in diameter, and particle size is again 3.3 to 5 microns. For the, you see, the width of the column. It has a higher number of theoretical plates, that is around 1 lakh. So they have micro columns, they have the high speed, and they consume very less solvent. Another type of column is a guard column. So as the name itself indicates, guard, it is guarding the main analytical or micro columns from the impurities, from some contaminants, which may permanently adhere to the analytical column and micro column. Therefore, they prevent the you see, spoilage of our main columns and increase the life of these columns. Now, resolution is greatly affected by the N. N is what number of theoretical plates. More is the number of theoretical plates, more will be the resolution. So in the previous discussion, we have impressed that resolution is the most important component of chromatographic experiment. right? So larger is the n, means larger is the number of theoretical plates, greater will be the resolution. And this plate number, right, it is or in general then it can be transferred to plate height also. It is related to plate height and flow rate. Right, so higher is the flow rate, higher will be the plate number. So resolution generally increases with increase in flow rate. So at the different particle sizes, like if the particle size of the silica is 3 micron or 5 micron or 10 micron, see here the plate height is decreasing. As the particle size is reduced from 10 to 3, the particle plate height is reduced with the change in flow rate. So at a particular flow rate, for example, here at a 2 ml per minute flow rate, when the particle size is a 3 micron, then the plate height is approximately here, it is around 5 micrometer. If it is a 5 micron, then it is around 10 micrometer. And if it is a 10 micron particle size, then the plate height is approximately 30 micrometer. So more is the plate height, more is the plate height, lesser will be the resolution. So this is the example of different particle sizes. So we have, you see here the different components, 1, 2, 3, and this is a chromatogram when the particle size is a 10 micron, and you see the peak shapes, and this is the chromatogram when the particle size is 5 micron, and you see the peak shapes, and this is the to resolution. This is a larger particle size, this is a smaller particle size, and see here the resolution is greater. Now, next to the HPLC is a UHPLC. UHPLC is nothing but ultra high pressure liquid chromatography. So in normal in HPLC, the high pressure liquid chromatography, the maximum certain pumps we can go up to 6,000 psi, but the particle size is 5 micron. So see here the resolution of the peaks, right? And if we decrease the particle size, right? Decrease the particle size, then the resolution is increased, right? And if we further decrease the particle size, the resolution is further increased. So what are the different changes which we are seeing here? When we are using the conventional HPLC, the total runtime is around 25 minutes, right? And when it is a UHPLC with a 3 micron particle size, the runtime is around 13 minutes, right? And when it is a UHPLC with 1.7 micron, then the runtime is around 6 minutes. So by decreasing the particle size from 5 to 1.7, the runtime has decreased from 25 to 6. So it is almost directly proportional. If it is a 3 times a decrease in particle size, there is approximately 3 times a decrease in the runtime, right? So if we are decreasing the runtime and resolution is not affected, right, then we are working on the performance, we are working on the efficiency. So if using this particular system, we can analyze 16 to 24 samples working 8 hours a day, right? And with this particular particle size, we can analyze 40 to 60 samples in the same period of time. And with this particular parameter, the particle size, we can analyze 90 to 120 samples in 8 hours. So efficiency is increased, cost effectiveness is increased, and over HPLC because it saves a lot of time, it saves a lot of energy, it saves a lot of man hours. Now, what is the, you see, uh, fundamental it's increase, the resolution increase. So this is the fundamental resolution equation where we see that resolution is equal to C n. N is capital N is the number of theoretical plates, and so this is some constant. Then alpha is your selectivity, and K is again a capacity factor. So alpha is a capacity factor and K is a selectivity. So these two components, they are the chemical one because selectivity and capacity factor of some any analyte, it depends upon the chemical interactions between the mobile phase and your analyte. And there's only one physical factor, that is the N, which is related to the stationary phase. So if we control this, we can control the resolution. So resolution is, we can say, directly proportional to the number of theoretical plates. So in UPLC systems or ultra high pressure liquid chromatographic systems, this increase in N or increase in the theoretical plates, right? This is the primary focus. So this is what HPLC, UHPLC is doing. Now this how this N is increased. So see here at the bottom, we have seen that there are in the bottom there total stationary phase length is L, right? This is actually how it looks like. But theoretically or hypothetically, this phase is divided into hypothetical plates, or we visualize this column or stationary phase as a combination of, as a collection of, or as a compilation of a different small number of plates, right? And each plate acting as a separate stationary phase. So if we increase the number of theoretical plates, right, it means the plate width will decrease. So this decrease in the plate width, right, this is the basic component. So if we decrease the particle size, this height equivalent to theoretical plate, or we can say the H will decrease. And this decrease in H means increase in N, right? Because N is what? L upon H. H is what? The height. So if the height is decreased, N is increased. If how the height can be increased? By decreasing the particle size. So if we decrease the particle size, we are increasing the number of theoretical plates. So if N is increased by 3 times, the resolution will increase by 1.7 times. So this is the relation which we have calculated from this equation. Now, improving resolution with smaller particle size, this is how. If we decrease the particle size, so number of theoretical plates are inversely proportional to the particle size. If the smaller particle size is there, number of plates will be higher. So if the particle size, in the last slide, we have seen that the particle size decreased by 3 times, let's say from 5 to 1.7, the number will increase by 3 times and the resolution will increase by 1.7 times. So this is again here a relationship between height equivalent to theoretical plate or the width of the plate and the mobile phase flow rate. So as see the flow rate is as the particle size is decreased from 5 to 3.5 to 1.7 or 1.8, the number of the height is or the width of the plate is decreasing. It means the number is increasing. So this part is highlighted because it shows that at a particular see the flow rate for a particular particle size, what flow rate is optimum to work with. So when we are working with the 1.7 or 1.8 micrometer particle size, we can work at a flow rate of 2.5 to 4.5 ml per minute or so on. See here again, if we are working on a 3.5 micrometer, then the flow rate has to be around 2 to 4. And if it is a 5 micron, then the flow rate has to be 1.5 to 3.5. So what is another thing, that as the particle size is decreasing, the flow rate is increasing. The range of the flow rate is increasing. Now the resolution or the speed and the speed of analysis at a constant column length. So if we take two columns whose length is same, and let's see how the resolution and the speed is affected. So at a flow rate of, let's say this is a 1, right? So smaller particles, right, they have a higher resolution and higher particle numbers, the higher number of theoretical plates, and at larger particle size, they have the lower number of theoretical plates and lower resolution. So optimum flow rate is inversely proportional to particle size, and peak width and sensitivity. So efficiency, or we can say N, is inversely proportional to the square of the peak width. Peak width means how short the particle is, and sensitivity means how means we have. Okay, so continue with this. So should I move to back previous slide?
So you can continue with this one only because this was a slide which you were discussing.
Okay. So peak width and sensitivity. So there is a relationship between the two. So peak width means how broad our peak is, right? So if our peak is broad, its height will be less. If the peak is sharp, its height will be greater. So the target of chromatographic separation is to get maximally height and peak with a minimum peak width. So the peak width will be small, the resolution will be large. And this width can be lowered, or resolution again can be increased by increasing the number of theoretical plates. So if you see again, 3 times a decrease in the particle size increases the resolution, increases the number of theoretical plates by 3 times, and resolution is increased by 1.7 times, right? And the sensitivity is increased by again 1.7 times. So more is the resolution, more is the sensitivity. Then another parameter which is important from the UHPLC point of view is back pressure. Uh, this back pressure uh, is directly proportional to the flow rate. More is the flow rate, more will be the back pressure. Uh, because as we are decreasing the particle size, we are making it more and more compact, and it is now it takes a lot of effort to make the mobile phase move through the compact system. If we fill a column with, let's say, balls of larger size, let's say we filled it with the pebbles, and we put water on the top of it, the water will easily flow through it. It will not stop. And if we replace that those pebbles with the sand, which is a very fine particle sand, and we put water on the top, then it will not immediately flow through it. It will take some time. It will take time to come to the bottom. So it means why it is so, because water is experiencing some you see back pressure from the stationary phase, means from the sand, right? So if we want to make it flow through it easily, we have to apply pressure on it. So how much pressure we are applying on the water, that is equal to the back pressure which is exerted by the stationary phase. So we call it a back pressure. So back pressure is proportional to flow rate, and flow rate is inversely proportional to the particle size, right, squared. So this is the change in pressure is directly proportional to flow rate into inverse of the particle size. So this is optimum flow rate is inversely proportional to the particle size, and if the pressure will decrease. So according to this equation, the pressure will increase by 27 times. If we decrease the particle size by 3 times, the pressure will increase by 27 times. That is a huge amount of pressure which is required. It means in UHPLC, what we need, the simple pumps which are used for HPLC, they will not work, right? We need special pumps. So this is another change in the hardware in UHPLC. This is the constant column length. Means the length is same for all the columns. It's like a 2.1 mm bore size and 50 mm column, means 5 centimeter column. And the particle size is a 4.8 micron, means a larger particle size. See here the chromatogram, it is having a runtime of 15 minutes. And when it is a 1.7 micrometer, means around 2.5 times, around 3 times decrease in the particle size. There is, you see, resolution is, the runtime is 6 minutes. So there is approximately 2.5 times the decrease in the runtime. But at the same time, see here the pressure from 354 psi, which is noted with a low particles, larger particle size, it is now 7,656 psi, right? Around 22 or 25 times a decrease in the increase in the pressure, and flow rate is increased. So this is you see how the column particle size that affects the sensitivity, the resolution. See the resolution here, the two peaks, they are here, the peak width is large and here the peak width is small. Here, see, it is not a baseline resolution, right? And here it is a baseline resolution. Here the peak is broad, here the peak is relatively sharp. So column length to particle size ratio. This is another parameter to understand UHPLC. Column length, what is the total column length and what is the particle size? If we take this ratio indicates the maximum resolution capability. Maximum resolution capability. For example, in the beginning, when the HPLC was, you see, came to forefront in 1960s or 1970s, the particles were around 10 micrometers and the columns were of 30 centimeter length. And see, the length and the particle size ratio was around 30,000. Then in 1970s, then in 1980s, smaller length columns were made available. Smaller particles were used for the HPLC columns. So again here 150 divided by 5, we get a 30,000 ratio. Then further decrease in the column length and now decrease in the particle size. So it is again around 33,000. So these are the 1970s, 1980s. This is how the HPLC has evolved, or how the particles have particle size chemistry has evolved, and proportionally how the runtime has decreased from 30 minutes to 15 minutes to 10 minutes. And after that come the you see era of sub 2 micrometer particle size, like 1.7, 1.8 or so. So it is a further decrease in the particle size, right? And but the length, but the particle and the length also. So it is around 29,000. Then again, under my 10 centimeter column, right? Then 150 centimeter, 15 centimeter column. So this is the comparison here. If we compare this one, 5 centimeter column with 1.7 micrometer particle size with the conventional one, the ratio is almost same and the resolution is also almost same, but the runtime has decreased from 30 minutes to almost 2 minutes, right? And so that increases the efficiency by 15 times. 15 times more samples will be analyzed, 15 times man hours will be saved, 15 times energy will be saved. And if we increase the length, if we increase the length from 5 centimeter to 10 centimeter, the ratio is increased and therefore the resolution is also increased, 2 times resolution. And similarly here, the resolution is further increased if we further increase the particle size. So the same length to particle size ratio for two columns will produce the same resolution, and the difference is the shorter column will produce separation faster, because if the column is shorter, it will pose a lesser of the back pressure. Now scaling of HPLC to UPLC or UHPLC separations, and here same length to particle size ratio is there. So this is the example of HPLC from 5 micron, 150, 3.5, 100, 2.5, 75. So this is the particle size and length. And if we see the ratio, it is a 3, it is a 30,000, it is again 30,000, it is again 30,000. So it is same. And resolution is almost same, 2.28, 2.32, 2.34. What is changing? The time from 10 minutes to 4 minutes to 2 minutes. And if it is a further decrease, particle size is a further decrease now from 1.7 micron, and we make the length 5 centimeter. So again, the ratio will be around 30,000 and the runtime is 1.1 minute. And the resolution is same, right? So if there are the two things which we can do. One is, if we want to improve the resolution, we have to decrease the particle size. And if we want to decrease the runtime, then we have to decrease the, we have to keep the length to particle size ratio constant. So we have to work upon the different UC permutations and combinations. What are our requirements? Whether we want to shorten the runtime, whether we want to increase the resolution, or how we can maintain the high resolution while decreasing the runtime, right? So working on all these possibilities, we have to select a particular column having a specified length and specified particle size and specified bore size. So speed also increases. This is what we are doing. As the runtime decreases, the speed increases. Sensitivity also increases. Sensitivity means what? How sharp the peak is. If the peak is sharp, it is easily detectable. To decrease the, to make it sharp, we have to decrease the width. So this is what we are doing. With the decrease in the particle size, we are decreasing the width, therefore the sensitivity will increase. So this is by 3 times decrease in the particle size will increase the sensitivity by 3 times. So this is again the same with the back pressure. So these are the basic differences between HPLC and UPLC. The particle size in HPLC ranges from 3 to 5 micrometer, whereas in UPLC it is less than 2 micrometers. back pressure is very high. Then analytical columns, most commonly is HPLC18, and here they are specified UPLC columns or UHPLC columns. Then column dimensions are different. So they are HPLC columns are quite you see large in comparison to columns in the UPLC. We have to decrease the column length in case of UPLC, because if we will not decrease the column length, the back pressure will increase significantly, and our hardware may not be able to support that back pressure, so the system may not work. So all the UPLC columns, they are usually of 5 centimeter length. Nowadays they are available in the 2.5 centimeter also. Maximally we use 10 centimeter for UPLC. Injection volume also decreases, because as the particle size decrease, the bore size decrease, the length decrease, it means the column loading also decrease. So we have to decrease the sample volume, and this decrease in the sample volume is then compromised by sensitivity, because we are increasing the sensitivity, so decrease in the injection volume will not compromise the sensitivity of the system. Column temperature, the UPLC systems can be operated at a higher temperature in comparison to UPLC, and usually it is required because at higher temperature the resolution becomes, the elution becomes faster. The total runtime, that is again the less, very less in case of UPLC than in HPLC. Resolution is almost same, 3.22, right? And the plate counts are significantly increased. So this is where actually UPLC is based upon. It is based upon the plate count. It's based upon the particle size. The differences in other way. So HPLC is used to separate different components of a compound through identification and quantification. It is one of the most dominant and widely used technologies for analytical laboratories, and maximum pressure, average runtime, we have already discussed. And UPLC, they are used to separate different components of a compound through identification, the same purpose. HPLC and UPLC, they have the same purpose. The only difference is UPLC, they have the better speed, they have a better resolution, they have a better sensitivity than HPLC, and the maximum back pressure is very high in comparison to HPLC. So these are some advantages of UPLC. So they require less runtime, they have enhanced sensitivity, they provide better selectivity and a dynamic range of LC analysis. Resolution is better, multi-residue methods are applied, speed analysis, quantify accurately analytes and related products. So these consumption of solvent is very less. Consumption of solvent is very less. See here, the flow rate which is used for HPLC is a 3 ml per minute, and here it is a 0.6 ml per minute. So if we are running it for 10 minutes at a 3 ml flow rate, we are consuming here 30 ml of solvent, and here we are 1.5 minute runtime, 0.6 ml per minute flow rate. So we are using just a 0.9 ml of solvent. From 30 to 0.9 means the 30 to almost 1. 30 times decrease in solvent consumption. So that is adding to the you see contribution, that is adding to the contribution towards environment safety. So we are not see these solvents, they are usually discarded, right? Although in a environment friendly way, but the environmental waste is created very less. 30 times less waste is consumed with the UPLC. So disadvantage, there's only one disadvantage, that is the life of the columns, because life of the column depends upon how much back pressure it is experiencing. Because particle size is very less in case of UPLC, the back pressure is high, so the wear and tear is very high, very large, and that leads to early spoilage or early death of the column. So column life is very less in comparison to HPLC. So that is the only disadvantage. Otherwise, It is all advantage. So these are the, you see, some examples where I have taken from web. Ultra high performance liquid chromatography, tandem mass spectrometry for rapid analysis of trace organic contaminants in water. So see here where they have analyzed around more than 20 components in a single run within 6-7 minutes, right? And you will be seeing here that some of the peaks are overlapping. So these peaks are overlapping, let's say K, L, and M. So here the K is carbamazepine, and is a fluoxetine, and M is a dexamethasone. They are overlapping, right? So the question may come in the mind that it is a resolution problem there. Yes, they are not resolved when we see it on a UV, but when we couple it with the mass spectrometry, when we couple UPLC with mass, now mass will detect three masses here, because mass will see three masses here corresponding to carbamazepine, corresponding to fluoxetine and dexamethasone. From those masses we come to know, right, how much what thing is present, and on the basis of an area, individual area, we calculate their concentration. So this is this is the advantage of coupling UPLC with mass. The same thing we cannot do in case of you see HPLC with when it is coupled with UPLC, when it is coupled with the UV spectroscopy. This is another example, multi-residue analysis of 90 emerging contaminants in liquid and solid environmental matrices by high-performance liquid chromatography tandem mass spectrometry, right? Where UPLC, MS chromatograms, they have detected 90 contaminants within 23 minutes, right? So this is the very highly resolved spectrum from the UPLC MS point of view. Thank you all. This is all about our UHPLC. So if you have any query, we can take up right now. Any query?
Yes, sir. Good morning.
Yes, sir.
Sir, you talked about back pressure. I have just one question, that in back pressure, is there any role of length of the column as well?
Definitely, definitely. As we increase the length, the back pressure will increase.
Okay. So in UHPLC, we are using less the column with which are of lesser length, right? So that
Yes.
means they will have lesser back pressure. But
Yes.
the effect of back pressure will be there. I mean, in both the cases.
See, we have to strike a balance, right?
Okay.
So in UPLC is basically based upon the particle size chemistry. Okay.
Right.
If we decrease the particle size, we are increasing the resolution.
Correct, sir.
Right? But at the same time, if we are not decreasing the length, we are increasing the back pressure. Right? Now, back pressure, as we have seen in that case, there will be 29 times or 27 times increase in back pressure. And let's say our HPLC system is operating at, let's say, 2000 psi. So if the same parameters, means same length to particle size ratio is maintained in UPLC, right, there will be 2 into 27 to 54,000 psi pressure.
Okay.
Right? So it is not possible to work at that pressure.
Right, sir.
Right? Under those circumstances, it will just act as a bomb. Right? So we have to decrease the pressure. How we can decrease the pressure? By decreasing the length. Okay, so we have maintained what? We have maintained a length to column, length to particle size ratio by lowering the particle size and by decreasing the length.
Right, sir.
Okay, now length, that ratio is, it means the pressure will be also almost same. There will be slight increase, but that will be more or less same, right? So back pressure is compromised from that point of, from that angle. Now, if at 50 5 centimeter length and 1.7 micron, we are not able to resolve the components. We are not getting a sufficient resolution, right? UPLC, we shift to UPLC for two reasons. One is to increase the resolution. Second is to decrease the runtime. Okay. Now, if we have decreased the runtime, but if the resolution is not increased, then for that we have to increase the column length. Let's say from 5 centimeter, we have moved to 7.5 centimeter column length. 2.5 centimeter is increased. That will result in slight increase in back pressure, which may be manageable by the pump. But that will increase the resolution by from 5 to 7.5, right? So that will increase the resolution by approximately 2.5 times.
Okay.
Okay.
Right,
So
understood.
Yeah.
Thank you, sir.
Most welcome. Any other query, please?
Good morning, Dr. Sir.
Good morning, Gauravji.
Dr. Sir, this part, you know that some functional groups are attached on these particles.
Yes, ligands.
Depending on the functionality,
Mhm.
Some may be amino groups, some amide groups, or some other type of groups.
Mhm.
These are attached to the silicon.
Mhm.
So, is there any problem of high pressure or solvent selectivity on this type of functional groups?
See, these ligands, we call it functionalization of a silicon layer, right? This functionalization of
Right.
silicons is done through covalent bonding. And covalent bonding is, you see, we cannot just break the covalent bonding by simple shear pressure. Okay. And the solutes, they interact with these ligands through non-covalent interactions. Right. So when the solvent is moving at a high speed, when there is a back pressure, right, the covalent bonds, they will not break because of this shear pressure or because of this back pressure or because of this flow rate.
Actually, sir, we are also applying temperature, higher temperature to the column. Compared to the
Higher temperature, let's say we are,
HPLC.
let's say we are looking at 50 degrees, 70 degrees Celsius, right? Now, at that temperature, of course, when we work at the higher temperature, the life of the column is compromised, no doubt about it, right? But it is not like that they will start bleeding immediately, right? It again further depends upon what is the pH of the mobile phase. If the pH of the mobile phase is, let's say, towards alkaline medium and we are using high pH, then that will definitely lead to, early degradation of the column. If we are using pH in the range of, let's say, 3 to 6, right, then that is quite where the silicon and carbon, silicon, nitrogen, silicon, carbon bonds, they are stable. They do not degrade, they do not break at this particular temperature. So they remain stable for a longer period of time.
Okay, sir. Thank you, sir.
Hello, Gaurav.
Welcome.
Hello, Gauravji. Your question is very, very, very relevant. And sometimes you have also done separation using amide columns. Means silica surface is having amide groups on it. And definitely the choice of the mobile phase, its pH, and the separation efficiency will be different than the C18 column or the normal column which we will be using. So because separation in HPLC or UPLC is dependent on the polarity of the solvent. If you can adjust the polarity of the solvent, that is, polarity means you are affecting the partitioning of the analytes in the column. That's what
Yes.
I mean to say. Means partitioning means separation. And if there is no separation, there will be no, yes, this what you call functionalization of the column is very, very challenging. And it plays a very important role in the separation. Now, another example I like you were asking, functionalization. Like there are some examples of chiral column also, and chiral columns like they are coated with cyclodextrin or some other chiral separators, and you can separate alpha trans and cis, or you can separate dextro or these D and L isomers very easily. And this their detection or analysis is not possible by uh, IR or by mass spectrometry, which are the most powerful tools as a detector for HPLC or UPLC. This is the great advantage of modifying the columns.
Yes, sir. Actually, we have, sir, आपको पता ही है कि we have seen bleeding of columns, might column after some time. So,
Yes, that depends on the means. If you don't wash it properly and you use a uh, pH, higher pH, then there is always bleeding of the column. There is always maintaining a right pH for the proper use.
yes, sir.
Bleeding sometimes comes if we don't select the proper polarity of the mobile phase. And because we are always running on hit and trial of the separation, means uh, if one peak is not coming good, we accept it, and if out of 5, 4 peaks are good, or one is little bit bleeding or having tailing effect, then we little bit compromise, and it depends on the polarity. Main is it's a game of polarity.
Yes, sir. Thank you, sir.
No, very nice, and you can work more. And, the field is very upcoming field, modifying the columns, developing new columns, and hacking of the new columns is very challenging task.
Yes, sir.
Any other question from the participants, because it is Saturday and you have a lot of time, and Dr. Gulshan as a very, very big expert is in front of you, and you can resolve your all queries and excitements. We tried to give you the presentation in the lab, but there were some problems, and we can solve it. But if you like, you can come any other day to the labs and have a look how the system works. It will be great. Thank you. You can ask any more question, any other participant.
So if there is a no query, then should we move to the next session? Okay. So we are moving to the next session. Okay, so screen is visible. Is it audio clear?
Yes, sir, it's visible.
Audio clear, no?
Yes, sir.
So the next component of the major chromatographic analysis we take is the mass spectrometry. And like we have discussed the theoretical aspects of the UHPLC in the previous one, now we'll be discussing about the theoretical considerations of the mass spectrometry uh, in this session. So this is an outlay of a typical uh, chromatographic system where see here is a mobile phase reservoir which is controlled by some controller gradient if you want to work with the gradient mode, and then they are fed to the pump, and the pump delivers this mobile phase at a very high pressure through injector, from where inject the sample into the column where the separation takes place, and each analyte it goes to detector where it is detected. Now, depending upon the nature of the solute, depending upon the nature, I am again having some problem with the internet on a particular system. You guys give me 5 minutes so that I change the system. Okay. Where the mobile phase is pumped through specialized pumps, which can work under a high pressure depending upon whether it is a type of UPLC or whether it is a HPLC. So that mobile phase is pumped through injector uh, into the column where the separation of separation of components in the sample, which is loaded into the column by this injector, takes place. And those separated components, they are fed into this detector. Now, what kind of detector is required? It depends upon the nature of your components. So the various detectors which can be used, that is UV absorbance detectors, fluorescence detectors, electrochemical, refractive index, conductivity, mass spectrometer, FTIR, and light scattering. So these are the different types of detectors which we can couple with the this HPLC with the HPLC system or UPLC system, depending upon what information is required, what nature is required. So mass spectrometer we have specified here because it is a universal detector. Like UV absorbance detector, it will be applicable for only those compounds which are having some chromophore which is absorb some light in the range of 200 nanometer to 400 nanometer. So if the substance, if our components, they are not absorbing this particular wavelengths, then this detector will not be useful. Secondly, the fluorescent detectors. This particular detector is used for those compounds which exhibit some fluorescence. So they are very specialized chemicals like anthracene. Then electrochemical detectors, they are used for those species which undergo electro-oxidation reactions. Then refractive index is used for those substances which do not absorb any light, which do not exhibit any absorbance or fluorescence in the above said for two detectors. So like sugars, like your cycloalkanes or saturated compound, saturated alkanes, they are detected by refractive index detector. Conductivity, this is again used for those components which exhibit some conductivity. So this is particularly for metal ions. And FTIR is a use for organic compound which are having a specialized functional groups. So out of this mass spectrometer and light scattering, these are the two universal detectors which can be used, which cover all the components. Light scattering is again having some its operational problems, sensitivity problems. Only mass spectrometer is a detector which can be used as a detector for any type of organic compound which can be analyzed, which can be separated by liquid chromatography. So what is the scope of this mass spectrometry? So first we have to understand what is a mass spectrometry and how it works. Mass spectrometry or mass spectrometer is you see, it's find applications in every field of science, be it chemistry, be it biotechnology, be it pharmaceutical, be it clinical, be it environmental, be it biological. So it is, you see, it can analyze any type of compound, be it of natural origin, be it of synthetic, be it in biological systems or physical systems or in chemical systems, right? Or in any sample, air, water, soil, right? So all type of samples, whatever the compounds are there, they can be analyzed with the help of mass spectrometer. So what is basically mass spectrometry? What we do? So it is an analytical technique that is used to identify unknown compounds and identify and quantify the known materials. So it is a qualitative as well as quantitative. And it has a very high levels of specificity and sensitivity. And it requires very minute quantities for the sample analysis, means it can work at levels of even picograms. And if the molecular weight is very high, it can also work at a level of femtograms. Now, mass spectrometer is a versatile analytical tool because its analysis time is very fast. It takes less than 10 seconds to record the mass spectrum of a compound. It's a high precision, high accuracy, and it allows simultaneous measurements of multi-component mixtures. As we have seen in the last session, that there are 90 components which are eluted within 23 minutes, and there were 3 or 4 components which were co-eluting. So simultaneous measurement of multi-component mixtures. So at one particular point, if there are 3, 4, 5 components, they can be measured. Then concentration from ppm to percent of wide linear dynamic range, so we can measure in any units or in any range. And it's a cost effective due to high sample throughput. Although the initial cost is very high, it's a very expensive instrument, but that expenses, they are very effective. It's a cost effective because high sample throughput, you can analyze, you see, hundreds of compounds in a single day on a mass spectrometer. So the journey of this mass spectrometer begins in 1906 when Sir J.J. Thomson in his laboratory in 1906, they discovered the electrons through his tube, which is called as a cathode ray tube. And for this discovery and related to it, he was conferred a Nobel Prize also. So cathode ray tube, what is found in that day, that if a beam of electron is allowed to pass through a vacuum, right, and if there is no charge, it will follow a straight path, and if a charge is applied, it will bend by a certain angle. This is the basis of mass spectrometry, means a charged species under the influence of a magnetic, under the influence of another charge, it is deflected, right? So that forms the basis of mass spectrometer. And this is the very first mass spectrograph, although nowadays it's called a mass spectrometer, and but initially it was called mass spectrograph. It's a hand optics. This is the optics of this first mass spectrograph designed by Aston. And see here, There are the slates of the particles, they are moving through it, they are deflected by electric field, and then they are entering into the magnetic field, and magnetic field again deflects them, they strike a particular point, a spectrum. So this was the very first mass spectrometer which was used. Now, what does mass spectrometer do? Mass spectrometry do. Mass spectrometry is a way to weigh the individual molecules or ions. So it weigh what is the weight of, what is the mass of the individual molecules or ions, and the mass of these tiny particles is microscopic. They are very, very small. Now, although we say that the molecular mass of water is 18, right? But one molecule of water actually weighs 10 to the power minus 22 grams. So this is the, you see, it doesn't mean that they have there is a weighing scale in a mass spectrometer. No, right? But it weighs those very, very tiny particles through some other mechanism, which we will see how that is converted. And this mass is expressed in terms of mass to charge ratio. The weight of the particle is measured in terms of mass to charge ratio. So if a molecule weighs, let's say around 1000 Dalton, Dalton is the units of the molecular mass, right? And it's a molecular ion, it is a protonated, let's say M+1. It gains one proton, so it gains a positive charge on this. So its a total mass is a 101, right? 1001. And the charge is 1. So 1001 divided by 1, that is a 1001, that is a m by z value. But if it has two charges over it, for example, this molecule, it accepts two protons. For example, in case of proteins, now proteins have multiple hydrogen accepting sites. So they can accept one proton, two protons, three protons, or four protons. So accordingly, they can be singly charged, doubly charged, triply charged, or quarterly charged. So if there are two protons are attached to the molecule, the charge will be 2. So it will be detected as not 1001, but it will be detected as 1002 divided by 2, 501. So this is how the molecules are, you see, detected in the form of ions in a mass spectrometer as a mass to charge ratio. So the basic components of a mass spectrometer are listed here. There is the first is the ion source, where the ionization takes place, and the second component is mass analyzer, where the masses of the where the samples are sorted, ions are sorted according to their mass. We can say it's a filtering device, right? And they are sorted on the basis of their mass by charge ratio, and then individual ion, it reaches the ion detector where those ions are detected, and then it is fed to the data system to give you the mass spectrum. So ion source and mass analyzer, these are the two most important, most critical components of any mass spectrometer. And the combination of these two governs the sensitivity, activity, or ionization of a molecule. This is the very first requirement. A mass spectrometer will work for a molecule only and only if that molecule is ionized. If a molecule cannot be ionized, it cannot be detected by a mass spectrometer. So that is the only limitation of mass spectrometer, that it needs the molecule ways. One is a molecule can lose an electron by certain method that we will see a subsequent discussion to form a radical cation. So this radical cation is nothing but an ion. So this ion is detected, and a molecule which is basic in nature can accept hydrogen ion to form protonated molecular ion. And a molecule, if it is acidic in nature, it lose a proton to form a deprotonated molecular ion, which is having a negative charge. So if a molecule is converted to a radical cation, right, and let's say its molecular mass is 300, so it will be detected at m by z 300. If it's a basic in nature and it accepts a proton, so it will be detected at 301, m by z 301. If it's acidic in nature, it will lose a proton and it will be detected at 299 m by z. Now, what this means? So depending upon what mode we are using for the ionization, whether we are using a radical cation mode, whether we are using a positive ion mode, whether we are using a negative ion mode, accordingly we determine the molecular mass. So if we are working with a radical cation, so a peak, if we determine the peak at, if we get the molecular ion peak at 300, it means the molecular mass is 300. In case of positive ion mode, if we get a molecular ion peak at 301, then we will subtract 1 from this. That one subtraction is for this hydrogen, which is added to molecule of hydrogen. If it is recorded in a negative ion mode, then we add 1 to this because one hydrogen is lost from the molecule. So again, it will be 300. So these ions, 399, they are not called ions, they are called ions or quasi-molecular. According to its molecular mass is called as molecular ion. So molecular ion and quasi-molecular ions. Now there are different ionization methods. The ionization methods, they are selected on the basis of what kind of solute we are analyzing and what is the requirement, qualitative or quantitative, whether we want to go for structural elucidation or we want to go for quantitative estimation. Basically, there are more than 4 techniques, but we are focusing mainly on the 4 techniques because these are the most commonly used in environmental contaminations or environmental analysis. Electron impact is a one, then fast atom bombardment, then electrospray ionization, and matrix-assisted laser desorption ionization. So for small molecules, we go for the electron impact. It is called as a hard method also. And for peptide sugars, when the molecular mass is up to 6,000 daltons, we go for fast atom bombardment and electrospray ionization. It can be used for small molecules as well as peptides and sugars. So we can use electrospray ionization for molecules having mass as low as 50 dalton to molecules having a mass as high as 200,000 dalton. So the range is very vast for the electrospray ionization. And nowadays, in almost all the mass spectrometric analysis, particularly in LCMS or UPLCMS, for the matrix assisted laser desorption, this is particularly for peptides and proteins or DNA, and whose molecular mass is up to 500 kilodalton, means 500,000 dalton. Now, how does the electron impact ionization works? How does electron impact ionization works? Now, in this case, the sample is introduced into the ionization chamber. We call it part of the instrument by heating it until it evaporates. So we have to convert the sample from solid to vapor phase. And that gas phase or vapor phase sample is then bombarded with an electron beam, which is emitted from tungsten filament usually, and that has an energy of 70 electron volt. And when such a high amount of energy is striking the molecule is shattered or it is fragmented into the fragments, and those fragments are then analyzed by the mass spectrum, by the mass analyzer, and then to the detector. Okay, so this is here a molecule right? How it is impinged by a high electron density, resulting in when it impinges a molecule, it takes away one electron from it. So one electron is lost, and you are getting a radical cation. Radical cation, because radical, they are highly unstable, so they undergo fragmentation to stabilize themselves, right? So form fragments, and each fragment is then sorted by mass analyzer and then detected by the detector. So this is a kind of a unimolecular type reaction, unimolecular type of ionization, where nothing else is involved in the ionization, only one molecule, an electron beam, that's it. So this is, you see, a schematic representation of mass electron ionization chamber. See here, this is inlet from where the molecules, the sample is injected into the chamber, and there are, see, filament which emits electrons, and these electrons, they are moving at a very high speed because there is a positive and electron trap. So electrons are emitted from here, they are attracted towards here. So there is a right angle collision. So from here, your sample is injected, and from here, the electrons are moving and they collide. And when they collide, they will be converted to ions. And those ions are positively charged, and there is a positively charged repeller plate. Now this positively charged plate does what? It repels these positively charged ions away from it, and there is a negatively charged plate, and this negatively charged plate attracts the positively charged plates towards it. As a result, these positively charged components, they move from left to right direction, and here they are again negatively charged plates are there, so they further attract, right? So this way the ions are X-related. So this is how the ions are produced, and they are from the ionization chamber to the analyzer. Another second type of ionization mode is the fast atom bombardment. In fast atom bombardment, the analyte solution is mixed with a very low vapor pressure liquid matrix such as glycerol, thioglycerol, or so on, and that liquid of around a very low volume, 1 microliter, is you see placed on. I show you the tip here. So this is a tip, right? And here, this is the fast atom bombardment probe. On this tip, 1 microliter of glycerol mixed with your sample is placed, and then it is bombarded with the fast moving atoms. Those fast moving atoms are nothing but argon or xenon. So when these fast moving xenon and argon atoms, they strike this, they transfer their kinetic energy to these molecules, transfer energy to the solvent as well as to the solute. Solvent means the liquid which we have added, like a glycerol, and the solute which can be, you see, which is a neutral species. So when this kinetic energy is transferred to the molecules, they undergo multiple collisions. And when the molecules, they collide themselves, they transfer charge from one molecule to the another molecule, resulting in the ionization of the molecules, of the solute molecules, of the sample molecules. And this way, once they are so converted to the ions, then they are deflected, they are dissolved from the plate by current, and they are moved to the analyzer. So this is a schematic representation of this fast atom bombardment source. So see here, this is the probe tip, right, which we are seeing here. And on this, we have placed the matrix mixed with the analyte. And here, this is the atom beam, which is impinging on this. And they are very fast moving atoms. So xenon, argon, they are generally used because they are non-reactive, the noble gases. And they supply their energy to this matrix. As a result, there will be collisions. and when there are collisions, there will be ionization, and at that point of time, this probe, the surface will be heated. When it is heated, it will dissolve these ions from it, and these ions will be attracted towards this collector plate. Now, if we want to analyze the atom positively charged ions, then we will maintain these focusing plates at negative potential, increasing negative potential, low negative, high negative, still high negative, and the maximum negative potential, so that positively charged plates are, positively ions are attracted towards the negative, are deflected from it. And if we want to analyze negatively charged ions, then we have to maintain them at positive potential. So like this, we can we generate ions using a fast atom bombardment. So this is also a hard technique. Hard technique means when the molecule ions which are generated, they are of a high energy. If they are of a high energy, they will undergo fragmentation extensive. And if the fragmentation is extensive, it means the concentration of the molecular ion or the abundance of the molecular ion will be less. So it may be difficult for us to know the molecular mass. But if we want to see the fragmentation pattern only, then we can go for the hard ionization techniques, because fragmentation pattern can be seen only when the molecule is fragmented to the different fragments using these techniques. But if our target is to identify only the molecular ion, not the fragment, then we have to go for the soft ionization techniques. So before that, there are some advantages of a fast atom bombardment over the electron impact. So it is rapid and simple, relatively tolerant of variations in sampling. It is a good for large variety of compounds, and there's a strong ion currents and good for high resolution measurements. But the limitations are also there. High chemical background defines detection limits. Now, background, from where this background is coming, from the matrix in which we are dissolving, dissolving the solute. Solute has to be soluble in the matrix. Only then it can be analyzed. This is another limitation. But glycerol, as the atom is being bombarded on the matrix, so molecule will get ionized, the solvent will get ionized. So there will be, can say, a background interference because of the solvent. It is difficult to distinguish between low molecular weight compounds from the chemical background. So that is a limitation, and it's not good for multiply charged compounds with more than 2 charges. So if they are triply charged or quarterly charged, then they cannot be detected by this, because that is a limitation. And the mass range is typically from 3,300 dalton to 6,000 dalton. Now, if our target is to identify the molecular ion only, we don't want the molecule to fragment, then chemical ionization is an answer. Now, chemical ionization is a soft technique, very soft technique, which produces ions not through collisions, but through chemical reactions. That's why it is called as chemical ionization. So in this case, the second species is ionized by high pressure electron ionization. Now, we are not impinging the electrons on the solute itself, but we are having a reagent which is usually gas, right? So that reagent gas is impinged by high pressure electron beam, resulting in ionization of those reagents. Those reagents, ions, then collide with molecules, and during collision, they transfer their charge from themselves to the molecule. As a result, the molecule becomes ionized. Now, because this molecule is ionized because of the chemical reaction, its energy is less in comparison to those molecules that are ionized by the electron impact or through the fast atom bombardments. And these molecules, they may undergo fragmentation to very little extent, depending upon the stability of the molecular ion which is produced. So the most common gas which is used in chemical ionization is methane. So see here, the methane is electronically impinged by electron. The methane is get converted to either methane radical cation or methyl cation, right, or methine cation, or so on. So there are different species which are possible. Then this methane radical cation, it collides with methane, neutral molecule of methane, and form CH5, which is a protonated methane, right, and the radical methyl radical. Now this CH5 positive, it is a highly you see unstable species, because a methane carbon cannot bear a positive charge. So this methane CH5 positive, it will react with M, your molecule, and it will transfer its hydrogen, excess of the hydrogen to molecule. So M will become MH plus, right? And the CH5 plus will be converted to CH4. So MH plus, right, means the protonated molecular ion or the quasi-molecular ion is produced by chemical reaction between the molecule, neutral molecule, and the charged or the protonated methane, right? So these are the other possible species which can participate in this chemical ionization mode. So this is how this chemical ionization mode works. See here, we have a reactant gas, which is usually methane. Other than methane, we can also use ammonia or tertiary butane. And here is the sample which is inducted. So first first the gas is introduced into the chamber, right? So here is the electron beam similar to the electron impact. So electron beam is generated. So this is the collector beam, right? And these are the repeller plates here, which are maintained at a positive potential. And the gas enters into this chamber and it will get ionized. Once it is get ionized, then we stop the electron beam and a sample is introduced through this. Now the sample enters as a gas phase and it will react with the ionized gas molecules, and those molecular ions which are produced, the quasi-molecular ions which are produced, they are attracted towards the mass analyzer with the help of accelerating and focusing plates. So this way the electron impact, this chemical ionization mode works. So its working is more or less similar to the electron impact only. So only point is there are two inlet samples. When we inlet reagent gas, we switch on the electron filament, and when we switch off the electron filament, then we introduce the sample, so that the sample does not come in contact with electrons but only with the ionized reagent gas. Now that another technique is atmospheric pressure chemical ionization. Now this one, what's the difference? What is the difference? Now this chemical ionization is working under a vacuum. So here it has to be vacuum, right? Here it has to be gas phase. So the sample has to be in the gas phase, the reagent gas has to be in the gas phase, right? So that only works in the gas phase. But if we want to couple this chemical ionization chamber with the, let's say, liquid chromatography with HPLC. Now in HPLC, the sample is in the form of solution. So if it is in the form of solution, then how to convert it to gas phase? So your CI, your chemical ionization chamber, is working under vacuum, and your liquid HPLC is at atmospheric pressure. So that's the two opposite things, vacuum and pressure, right? So they have to bring into an interface which can couple the two, vacuum and the high pressure, right? So if we somehow we can modulate the design of this ionization chamber so that the chemical ionization can take place at atmospheric pressure, then that particular mass spectrometer can be coupled with the liquid chromatography. So this is the, this is the major component of LCMS. There has to be an interface which allows the entry of liquid into a vacuum system. So APCI is a atmospheric pressure chemical ionization. So when we do the chemical ionization at atmospheric pressure, we call it APCI. So APCI is a gas phase ionization process. Again, it's a gas phase only. And here, it nebulizes solvent stream with the coaxial flow of nitrogen and adds heat to desolvent the aerosol so that all species are in gas phase. So this is how it is done. See here, the analyte is not in the, we are not using any reagent gas. We are not using gas phase ions. So this is your stream, the white one. It is nebulized. So how it is nebulized? You have one stream, and out of that you have one capillary, and there is another capillary around it. So from the outer capillary, nitrogen is flowing, and from the internal capillary, your solvent is flowing, right? So when this flow at a very high pressure, nitrogen flows at a high pressure, it converts the liquid stream into spray, and that spray contains your sample, your solvent, as well as your molecule, right? And now ionization produce these get ionized, and then they get ionized. They get they react with the solvent mobile phase. Sorry, your molecule, and this molecule is then ionized. So this is how it happens. Yeah, this is your solvent, and it reacts with your molecule, and your molecule gets ionized. So this is the atmospheric pressure chemical ionization. So it has transformed the application of liquid chromatography in every field of science, because many samples are in the liquid phase, not in the gas phase. So so this APCI, although the application of APCI is limited, but electrospray ionization, that is again, you see, a revolutionary technique developed in the chromatographic analysis. It was, you see, developed by Fenn, a scientist who was, you see, conferred with the Nobel Prize also for this particular discovery, for this particular invention. So ionization process is carried out at atmospheric pressure ionization, and it involves a spraying a solution of the sample in a suitable solvent. The same thing, process is same. So here we have a sample flow, and here you have a nitrogen flow. So there's a dual capillary, and when it is converted to spray, and now how the ionization takes place. So we are not using any electron beam here, right? But these ends of these capillary, the outer capillary, they are maintained at a high voltage. So this high voltage, so when the molecules are passing through this capillary, which is maintained at high voltage, it will induce collisions, and those collisions will tend to ionize the molecules. And those ions, now this is converted to spray. Now spray is is a droplet. Now droplet is a droplet of solvent, and in that solvent, what is the soluble? Our sample. Now the sample, these are analyzed, these are ionized. Sample solvent is ionized, as well as your sample is also ionized. Now these drops are formed like this. These drops are formed, right? And this chamber is heated. This whole chamber is then heated. And when with this heating, the solvent will evaporate. If the solvent evaporates, the droplet size becomes smaller and smaller. They become smaller and smaller, and as a result, the charge density increases. So larger drop to smaller drop to smaller drop to smaller drop. The charge density increases. So when the particle size, this droplet size, it becomes almost dry aerosol, right? And the dry aerosol, the charges are all are positively charged, so there will be charge repulsion, and it will burst. It will burst into individual molecules, individual ions. So those ions are produced. And this is at atmospheric pressure, okay, and this is again atmospheric pressure, and the analyzer is maintained in vacuum. So here is a pressure, here is a vacuum, so the ions are sucked into the analyzer. So this is you see a vacuum interface through which the molecular ions they enter into the mass analyzer. So this is how it looks like. This is a probe, needle probe. It is this part of the instrument. So it is a doubly tip. So this is the outer tip, and there is an internal capillary, and the nitrogen is flowing through it. And this is maintained at high pressure, high voltage. And this is how a jet, first a jet is formed, right? Jet of ions, and then because of this, it is converted to spray, and this spray is then heated. Because of this, the temperature of this chamber is increased, and they are converted to dry mist. So this is how electrospray ionization takes place. Now, electrospray ionization, it can be operated in two modes. One is a positive electrospray ion. In positive electrospray, for example, this is a lidocaine, which is a basic molecule. So nitrogen has a lone pair of electrons, so it will accept hydrogen and it will be protonated. So this is a positive ESI, means when an molecule accepts a hydrogen ion, we call it a positive ESI mode or positive electrospray ionization mode, and the molecules are detected at 1 mass higher. It can be also worked with the negative ionization mode or negative electrospray mode for particularly acidic molecules, for example, ibuprofen, which is having a hydro OH, acidic proton. So this acidic hydrogen is removed and it is converted to negatively charged ion. So it is detected as M minus H. So these are the how the molecules are ionized with the help of electrospray ionization technique. Now there are several characteristics of the ESI mass spectra, and out of the LC-MS experiments or the analysis which are involving LC-MS instrumentation, more than 90% experiments, more than 90% analysis are being done with the LC ESI mode, only ESI, and only for very special molecules we go for MALDI, or molecules which are having a mass of less than 1000 Dalton, they normally give a singly charged ions. But those which are having more higher molecular mass, they give multiply charged ions, for example, proteins and carbohydrates, high molecular weight carbohydrates. The ESI is a very soft ionization technique. Even non-covalently bound molecules can be detected very intact. So because it is again, what we are not impinging the molecule with electron. So the energy of the ion is not very high. That's why we call it a soft ionization technique. Means the ionization technique is very soft on the molecule, very soft on the molecule, right? The last technique is the MALDI, matrix assisted laser desorption ionization technique. This is see here what we do in matrix assisted laser desorption. Sample is mixed with the matrix, which is similar to, you see, as we have done in the fast atom bombardment, but there are the other matrix can be also used. And but these matrix they have to be some vapor pressure sufficient so that they are deposited as a film on a plate, right? So they are deposited on a plate, and this plate is maintained at potential, high potential, and then a laser beam is incident on this plate where the sample is deposited, right? And sample induce laser induce heat. That heat will induce collisions, and those collisions will induce transfer of hydrogens from matrix to from matrix to molecule, or from molecule to matrix, depending upon the nature of the molecule. So accordingly, we get a protonated molecular ions molecules which are detected then by the detector, right? So this is the how the MALDI works: matrix assisted laser absorption. So first is a matrix, then is a laser assisted, and desorption occurs because of this heating. Ions are produced, this plate is heated, and they dissolve the ions. So we have seen the different ionization techniques, and depending upon the molecular weight, depending upon the polarity of the analyte, we can select appropriate ionization technique. And if we see the most versatile and the most wide range which is covered by any technique, that is a electron spin. See here, it covers all molecular masses and almost all polarities. So they are covered. Okay, so this is various ionization. The second component of a mass spectrometer is a mass analyzer. Now, this is again very important component. As I said, ionization chamber and a mass analyzer, these are the two most important components, and they define their specificity and sensitivity. Now, mass analyzers can be simple quadrupole, triple quadrupoles, ion trap, or TOF, or hybrids. They are the most generally used nowadays, but traditionally we used to have magnetic sector mass analyzers and double focusing mass spectrum mass analyzers. Those analyzers, double focusing mass analyzer and magnetic sector analyzer, they are used when we want to record the simple mass fragmentation of a pure compound. But if we want to analyze, let's say, some components in a sample, then we need both qualitative and quantitative information. And for that, quadrupole or TOF or quadrupole TOF hybrids, they are the most widely used. So quadrupole, what is a quadrupole analyzer? So quadrupole analyzer is basically composed of 4 poles. There are 4 poles like this, right? There are 4 poles, and the 4 poles are arranged such a way that the opposite poles, they are maintained at the same potential, same polarity. They are having the same polarity. For example, these are the 2 opposite ones. They are having the same polarity, and this is the another opposite. They are having the same polarity. So these two are maintained at let's say DC potential, and they are maintained at alternating potential, alternating current. So a DC and frequency both are applied, and so alternating and direct. And when the two are combined, so in this region, an alternating current field is generating. A field is generated which is oscillating at a particular frequency. That frequency of that field depends upon the intensity of this DC and this RF amplitude. So depending upon that, so how the samples are then separated. Now this whole region is having a direct current as well as RF. It means it is a vibrating, it is having a particular frequency, right? So when a charged particle moves through an electric field, it is deflected. This is the basis of mass spectrometry in that cathode tube, what we have seen. Then it is deflected. So it has to pass through it. It has to travel such a way that it does not strike the poles, but it oscillates. It oscillates with the same frequency that it oscillates. This field is oscillating. So see here, there are the different masses, right? And these different masses, they are having a oscillating frequency which is different from the oscillating frequency in these 4 poles, right? And they strike the poles. and there will be only one mass at a particular combination of DC and RF, which will oscillate at the same frequency at which this field is oscillating, and that will pass through. So we vary this DC and RF systematically so that every mass is allowed to pass through it one by one. So this way the sorting takes place. So first one mass pass through it, and second mass pass through it, and then third mass or fourth mass or so on. So this is called as basically mass filter. So because it is having 4 poles, so it is called as quadrupole. So this is how a quadrupole instrument looks like. So this is your ionization chamber, and from this ionization chamber, you convert your molecules into ions, and those ions are then fed into the quadrupole. And in this quadrupole, this analyzer, which is again maintained at you see very high vacuum. It has to be under high vacuum, because if it is not vacuum, then the air will result in collision with the molecule ions, and the ions will be destroyed. So they will not reach the detector. So let's see, the pressure is very, very high, very, very low, 1.3 into 10⁻⁵ millibar. So very high vacuum is maintained, and this vacuum is maintained around the clock, 24 hours. The vacuum pumps, they go on working 24 hours in a mass spectrometer. So this quadrupole is here, and every ion reaches the detector, which is a diode, and it will produce a response. And with every striking, it will give you a response, and that response is converted to mass by charge ratio based upon what current and what radio frequency is fed into this. So that's how you see such tiny masses are weighed, how the mass spectrometer weighs such tiny masses. So this was a single quadrupole which we have seen. Um, there is another term which you have heard many a times. We call it a tandem mass spectrometry, or MSMS. Now, what is this tandem mass spectrometry? Or it is achieved through triple quadrupole analyzer. So there is not just one quadrupole. There are 3 quadrupoles attached in series. So basically the basic component, basic function of a quadrupole is to filter the masses according to their masses, filter the ions according to their masses. Then in quadrupole, what we do, we have the first quadrupole which act as a filter. So let's say the 2 ions are fed into the first quadrupole, and we allow only one mass to pass through it. Okay, that mass, that ion enters into the second quadrupole, which is not maintained under vacuum. It is under high pressure, right? It is with an inert gas, usually helium or argon, and because of the collisions, this ion will fragment. And those fragments, all those fragments are then fed into the quadrupole, which is maintained under vacuum, and that quadrupole will sort the fragments ions according to their mass, right? So this is a mass filtering, this is a collision cell, and this is again mass filtering, and having 3 quadrupoles, right? So it's called as triple quadrupole. So this is how a triple quadrupole looks like in the instrument design. Ionization source, then fed into the first quadrupole, and then this is the second quadrupole. We call it a collision cell, which is maintained under pressure, and here it is against third quadrupole, and then the detector. Now this quadrupole has the capability to detect only the masses into the nominal mass. Ions with the nominal mass or the unit mass. For example, carbon, hydrogen, oxygen, and so quadrupole instruments so the quadrupole instruments, they detect the ions, they detect only the nominal mass. Means let's say carbon monoxide, nitrogen, C2H4, ethylene, and CH2N. They all have a nominal mass of 28. So quadrupole will detect these all four molecules as only 28. So it is not able to distinguish whether it is a carbon monoxide or nitrogen gas or C2H4 or CH2N. So it is not able to distinguish. It is not able to distinguish as a molecular formula, right? So for to distinguish the molecular formula, what we need the exact mass of the species, right? So this is how a mass spectrum is recorded in a quadrupole system. See here, ketoprofen, flurbiprofen, ibuprofen, different kind of NSAIDs, painkillers which are used. So their mass is recorded only up to 1 decimal unit, which is of a no value. So it is a nominal mass. Similarly, this is a MS-MS spectrum of propanol. MS-MS means using triple quadrupole. Now, triple quadrupole means where, let's say, we have allowed the mass of 260 to enter into the second quadrupole, and in second quadrupole the 260 fragments, and those fragments, they are analyzed by the third quadrupole, right? So 218 and 183, so these all are fragments, and this pattern is called as this spectrum is called as mass spectrum of the molecule, and this is the fingerprint of a molecule in a particular ionization condition. So if we are recording the mass spectrum of a compound, for example propanol, in electron impact mode, it will have a particular fragmentation pattern, so that is a fingerprint. Similarly, if we record the mass spectrum of a propanol in ESI mode, then it will be a fingerprint of that propanol in ESI mode. So therefore, they are used for the qualitative purposes from that point of view also. Another type of analyzer is the time of flight. Time of flight instrument, it works on the principle that how much time is required for an ion to reach from, to travel from its origin till detector. So let's say we are getting all the ions from the ion source. We have obtained all the ions from the ion source, right? And there is a pusher plate. Pusher plate is maintained at, let's say we are generating positively charged ions. So this pusher plate will be maintained at positive pressure, positive potential, so that it pushes the these ions. So when it pushes the ions, now we are maintaining, we are giving a uniform energy, an equal energy to all the ions, and all the ions, they are having different masses. So the kinetic energy of every mass will be same. Kinetic energy will be same, because kinetic energy is equal to mass is half mv square, mass into v square upon 2, right? So that is the kinetic energy. So kinetic energy is same, but masses are different, so their velocities will be different. So the mass is higher, right? It is a ion, right? Its velocity will be less because kinetic energy is same. And if we are having another molecule, another ion whose mass is less, right, then its velocity will be high. So a low molecular ion will travel at a high speed, whereas a high molecular weight ion will travel at a low speed. So when they pushed, they travel at a different speeds. So a low molecular weight ion, which is the red one. So just see again, right? So red one is smaller, green one is larger, and blue one is the largest. So red one, because its mass is less, its velocity is maximum. Red followed by green and then blue. Then accordingly we get a mass spec. So this is how time of flight instrument works. So this is a TOF instrument, right? This is a TOF. Actually, this is not simple TOF. This is a Q-TOF, quadruple TOF. Actually, TOF is simply TOF is never used. It is always used in combination with quadrupole. It can be single quadrupole, it can be triple quadrupole. Usually it is with a single quadrupole. The purpose of the quadrupole is first quadrupole analyzes, second collision cell, and moves they go to the TOF. Now the TOF in TOF, these ions, they travel a path from its origin to then there is a repeller plate and then to the collector. Now this repeller plate is again added to increase the flight path. Larger is the flight path, larger will be the resolution. Like in UPLC columns, we have seen that if we increase the length of the column, we can increase the resolution. Similarly, if we increase the flight length, right, we can increase the resolution. With this resolution, with this time of flight, we can now work with we can find out the exact mass. So what is the difference between nominal mass and the exact mass? The advantage of the TOF is that we can detect a molecular formula or molecular composition from its spectrum. How? See, we have seen the 4 examples: carbon monoxide, nitrogen, ethylene, and CH2N. Now they have a nominal mass of 28, but the exact mass of nitrogen is not 14, it is a 14.0031. Similarly, the exact mass of carbon up to 4 decimal point is different, right? So when we see the exact mass of nitrogen is 28.0061. For carbon monoxide is a 27.9949 or so on. So they are all the 4 components that are having different exact masses. And time of flight analyzer is the only component which can, or there is one orbit trap also, which is more sensitive than time of flight. But time of flight is having sufficient accuracy that it can distinguish the masses up to 4 or 5 decimal places. So we can see the exact mass. If we know the exact mass, we can do what it is. So if we have, let's say, if I had a sample which contains nitrogen in it, so it will show you a signal corresponding to a M/Z ratio of 28.006 minus plus minus 0.0002 or 3 or 4. So that is the accuracy, that is a precision, which is very much specific to time of flight analyzer. So see here, we can, this time of flight analyzer is able to distinguish 11.39.105, 130, 155, 180. So this is a very close resolution, which is possible only with the time of flight analyzer. So this is another example. This is just an example where 402 pesticides are analyzed, dissolved in a single run, right? And that run is just 14 minutes. So within 14 minutes, using TOF, using QTOF and UPLC coupled with the QTOF, we are able to identify, quantify 402 pesticides. Thank you. So these are about basic concepts or the theoretical concepts of mass spectrometry. So if there's any query. Is there any query? Any party, any query?
Anyway, if any question, they will ask I thank you, Professor Bansal, for a very informative talk.
Thank you, sir.
And
So we will be again joining at 2 o'clock, right? There is a session from Professor Yolanda. She will be again talking about analytical techniques of inductively coupled plasma mass spectrometry and gas chromatography mass spectrometry. So it is quite related to it. So the participants will be having more information about these techniques.
okay, sir, we meet again.
Okay, sir.